Hi, everyone. Welcome to this week's seminar series. It's our pleasure to welcome Dr. Nikolaos Bouklas as our speaker for this week. He's an associate professor in the Sibley School of Mechanical and Aerospace Engineering at Cornell University, and also serves as the director for research in CAD, CAE, and machine learning at Pasteur Labs. His research lies at the intersection of computational solid mechanics and scientific machine learning, where he develops theoretical frameworks and advanced computational methods to deepen the understanding of material behavior and improve predictive modeling for complex engineering systems. Before joining Cornell, Dr. Bouklas was a postdoctoral researcher at the Laboratory of Multiscale Material Modeling at EPFL, Switzerland, and at the Odin Institute for Computational Engineering Sciences at the University of Texas at Austin. He earned his PhD in aerospace engineering and engineering mechanics from the University of Texas at Austin, and his diploma in mechanical engineering from the Aristotle University of Thessaloniki, Greece. A recipient of the Air Force Office of Scientific Research Young Investigator Program Award, Dr. Bouklas has also held leadership roles in Cornell Scientific AI Center, which is funded by the Office of Naval Research. Now, with that brief introduction, please join me in welcoming him for this talk. So it's all yours, Nikolaos.
Thank you, Subdata, for the intro and for the invitation. So the talk has a title that might mean something to some people, might not mean something to some others. So it's pretty nondescript, and it is from local to non-local models in continuum mechanics. And pretty much I'll try to do an overview of how SciML has influenced this research direction in the past 6 years in my lab, and what I consider to be the next things to do, right? So it's I would say that 2/3 of the talk have to do with things that we have done with SciML, and the last 1/3 is related to open questions that I think we're going to have to tackle in the next few years. So I'll skip the outline, but for the most part, we'll focus on some data-driven approaches. Then we will do some focus on some physics-informed approaches. Connect on how some transfer learning schemes, bringing together solvers and surrogates, can help us achieve some of these goals that we want, and also open problems for more complex material systems. So my motivation, and especially the context in which I think AI tools can assist the field of computational solid mechanics, is that there are several tasks that where they can assist. One is acceleration of computations, interfacing with experimental data. For me, this is one of the most important ones. Inverse problems and parameter estimation, and then uncertainty quantification and propagation. For example, here are some surrogates that we had developed in my lab for subsurface flow in media that have different type of porosity, and also some schemes for two-scale phenomena happening in structures where you have some macroscopic structure, and then at every Gauss point, for example, of this finite element model, you have to go to some microscale RVE and obtain some more information. Pretty much this was something that was done with finite element square methods in the past, and now SciML tools are really assisting, helping the closure from the microscale RVE to then transfer the information to the higher scales. Now, regarding these closures, right, and regarding computational solid mechanics in particular, there are some necessary ingredients that we need to solve problems in mechanics, right? So we start usually by defining our kinematics, our constitutive laws through thermodynamic constraints and mechanistic intuition many times. And then we have our governing equations, again, through balance laws. And usually the bigger question in mechanics, right? So in fluids, we usually have very hard equations and simpler constitutive laws. In solids, it's the other way around. Our equations are simpler, but the constitutive laws is where the complexity of the material system is hidden, right? And there's three prevalent approaches for constitutive modeling. One is phenomenological. Phenomenological means that you see a phenomenon, you observe it, and then you describe it with logic, with mathematics, right? The other one is micromechanical, where you can have a lower scale representative volume element or statistical volume element, and you can derive some expressions, either analytical or numerical. The third one is purely data driven. If you have some data and directly work with that, and there's a lot of work in this direction as well. And then the options for the solution of governing equations, right? One is if you have analytical tools to solve them, right? If you have some full order model to solve them, and here I also, I have finite elements, finite differences, fast Fourier transforms, but I also put in here physics informed neural networks, because here you work directly with the with the governing equations, right? So it's not necessarily some data driven approach, even though you can embed data in it. And then you have reduced order models, and there are intrusive and not intrusive data driven approaches. And I consider a lot of the operator learning approaches that have been recently used and prevalent in our community in this bullet point as well. So now, for constitutive modeling, usually the elephant in the room is always the data, and you have to understand where the data comes from and what is captured by the data, because sometimes, like with large language models, that what dictates the efficiency of our approach is the access to data that we have, right? So the traditional approach in mechanics is to have some simple mechanical test, right? This is the first line, and there are four categories here. So here we have a macroscopic response, and we have access to that. For example, that would be a stress strain curve. You don't have full field information, but here these experiments usually are constructed such that you have a homogeneous stress state. For example, this could be uniaxial testing or biaxial testing or single shear or some type of volumetric test. Data availability is low, and data availability is low because of the specific reason that I mentioned before, that we have access to only specific stress states. So if you're thinking of accessing information in a variety of stress state, which is usually a predictive model that we're going to deploy in a finite element setting to do design, is going to access many complex stress states. Once you start building a complex structure with complex geometry, this geometry is going to lead every material point in this structure to experience a more and more complex stress state. So here we have low data availability, because if we're thinking in stress space, we're only accessing, if we have one of these experiments, we're going to access one line in that stress space. And we don't have access to internal variables, right? So if we think of experiments then with better access to imaging, right, like digital image correlation experiments, then we have the macroscopic response here. This is a biaxial test. You see this cross type specimen and this region in the center where digital image correlation is mapping the strain field. We actually have full field information, could have displacement or strain on the surfaces. Of course, we don't have, in something like digital volume correlation, you could get volumetric data. But again, data availability is now partial. That means that you don't have labeled data pairs. You don't have stress and strain like what you had in the previous type of experiment. Now you have access to a strain field or a displacement field, but you only have access, the force type quantity that you have access to is only macroscopic. And again, there's no access to internal variables. Now, once you start thinking of more complex imaging approaches, like high energy X-ray diffraction experiments, where here you have some X-rays that are passing through the structure of the specimen. Here, one could think of some polycrystal metal specimens. You can think that you have the macroscopic response again. You can have the elastic strains for each grain, but the data availability again is partial because there is no direct access to plastic strain. So access to internal variables, again, it's limited because we have partial or indirect access to the evolution of the plastic strain here. Now, one final one is thinking that we have some computational representative volume element. Here again, you can consider polycrystalline structure. And this RVE now we can load in any mode that we want. So we have access to macroscopic information, full field information on the surfaces and in the volume. We have access to internal variables because we have chosen a model, but again, data availability is again limited, right? And I'm saying limited because if this is a very simple RVE and the constitutive laws of each grain is very simple, then maybe you can do a lot of stress states. But you can imagine that as we're considering history-dependent responses, it's very hard to sample that space of responses. So you have to sample in stress space and you have to sample in some type of rate space in order to get all the data in different histories. So this is it again very quickly becomes computationally very demanding. So now when we started on this topic 6-7 years ago, especially the data-driven approach, and I'm saying that this was maybe a naive approach that we had at the time, was that we were trying to map strain to stress. This is the second Piola-Kirchhoff stress, and this is the right Cauchy-Green deformation tensor. So we wanted to learn this major mapping, to learn this closure, right? To have thinking that we have some information for between stress and strain data pairs, and we actually want to just use this data to run finite element simulations to run at the structural level. And now you could also learn the minor mapping, which has to do with a consistent tangent, right? And we were mostly thinking of having a computational RVE. So this is how we started, right? So we thought that we had a system where we could generate pretty much any type of data that we wanted. And even though the elephant in the room is always, how much is that going to cost? How much time is that going to take on our server to generate all that data? And then at the end of the day, we end up with n samples here that have strain, stress, and the tangent information. And we started trying many different methods, right? And maybe our implementations back then of how we approached it were not as mature as they are today. But what we found at that point was that we had started with k-nearest neighbors, artificial neural networks with gradient information as well, Gaussian process regression, and here specifically this was a flavor of local approximate Gaussian process regression, right? Where depending on the neighborhood in strain space where we would construct a local GP. And we saw at that point, we were still thinking that, we wanted our methods to converge, to show some convergent behavior as we increase the data. And this was the total error between all samples that we were generating. And we were actually happy with this local GP on how it was behaving. And I will try to bring up the benefits and the deficiencies of this approach, right? The deficiency is obvious that here, do we actually want it to converge as we go to higher and higher data points? Should our goal be to handle more data? Because as we said before, the elephant in the room is that we usually don't have all that data that we want in mechanics. And then once we learned this with this local GP, the point was also to pass it to finite elements. So we had to figure out how to make these to see convergence if you try to do a Newton-Raphson iteration at a Gauss point. And we saw that we were having some challenges for convergence with k-nearest neighbor neural networks where we had some linear or sublinear convergence. With our LA GPR, with our local approximate GPR, again, this was freezing, so we had to modify our Newton-Raphson scheme, which had to do with freezing this local neighborhood after some point. So we just had to stop updating the local GP to obtain some linear convergence, and then we trained this also on RVs that had 25,000 elements for some particulate two-phase microstructure, and we trained in a almost 20% training domain. So all the components of the deformation gradient could change by 20% about the undeformed state, and we considered the two phases, both the matrix and the particles, to be Neo-Hookean. And we had our server running for a couple of months, generating all that data. And at the end of the day, we were able to run structural simulations that showed convergence that was between linear and quadratic for standard tests in solid mechanics, right, for the punch test and for Cook's membrane. And we were pretty happy about it. But should we be happy with this? Because there were a lot of things that we neglected, right? So we forgot about the physics as we were doing this. So if we're in the context of hyperelasticity, we can repeat Clausius-Planck inequality that now becomes an equality, and this requires the second Piola-Kirchhoff stress to be written as a sum over gradient over derivatives of the energy, the free energy density, which in turn here is a function of the right Cauchy Green deformation tensor, and also these structural tensors, these A1 up to AP. These structural tensors are, in the context of anisotropic hyperelasticity, are structural tensors that describe the character of the anisotropy of the material. And they have to do with the directions of reinforcement. For example, in a transversely isotropic material, this A1 would just be the direction, the dyad of the direction of the fibers with itself. And then what we have here in the sum is the derivatives of the free energy with the invariants, right? And here we have the invariant, the mixed invariants, right? We have the principal invariants of C, but we also have the mixed invariants that come up with the combination of C and all the different structure tensors A. And then we have the derivatives of the invariants and the right Cauchy Green deformation tensor. And here you see that this is a scalar quantity and this is a tensor quantity. And these tensor quantities here are actually known, right? Because we know the derivatives of invariants with the right Cauchy Green deformation tensor. These scalars is what is unknown. So now we can actually form an integrity basis of symmetric tensors H, and we can call this basis G, and we have a representation theorem for the stress, which can be expressed as such, right? So we have coefficients lowercase c1 up to cd that are functions of the invariants, and then these components of this tensor basis H. Okay, so here one can understand, since H is known, the only thing that we have to learn now, instead of learning a map directly from C to S, we can learn the map from invariants to these lowercase coefficients. So this was what we were actually going for, and we were happy when we got this result. So for example, here we just generated some synthetic data from the Mooney-Rivlin model, compressible Mooney-Rivlin, and the blue line corresponds to the naive mapping we were doing before that was just data-driven. And for example, here we had up to 4,500 data points. But then when we were doing this invariant mapping, whereas now we would just have to learn coefficients, if we were just using this, we would just have a mapping from the invariants here to the C's, right? And this here is isotropic, right? So the invariant base here, the integrity base here is I, C, and C inverse. Okay, and we saw that the error dropped up to 1 order of magnitude. So here the two different dashed lines had to do with trying to sample as uniformly as possible in invariant space, even though we were initially sampling in the formation space. So we had to do something like some simulated annealing to sample uniformly in invariant space. And we saw that we pretty much dropped the error by an order of magnitude, right? This total error over all samples that we were generating. But then also we saw that we actually also dropped about 1 order of magnitude in data that we needed. Okay, so here, for example, when we used 180 data points, we still had a significantly lower error than when we used 5,000 data points in the blue scheme, right, in the naive scheme. So we saw that this was actually very promising, and this is what we were hoping to achieve. What we were not hoping to achieve, and we were quite surprised from, was when we were testing then on unseen data. For example, this was some constrained tension experiment, and where the truth is the magenta. We saw that when we used our naive scheme, the moment we were leaving our training domain, remember that we trained in this 20% domain, so around F11, about 20%, so the two vertical dashed line represent the domain in which we trained. The moment that you leave that domain, our traditional purely data-driven approach was falling apart, which is what you expect, right? So in machine learning, extrapolation and generalization is something that's very hard to do. But somehow, even though this is not what we were aiming for, we saw that we could extrapolate, right? So we have this fine black dashed line, and we saw that this actually extrapolated very well, much further out. I'm not implying here that one would want to deploy something much further out than the training domain, but actually the model is not falling apart the moment you start extrapolating. And now again, the elephant in the room is the data. In this case, we had uniform sampling. Sometimes if you have very, very sparse sampling, interpolating between very sparse data, things like, so you want to be able, when your interpolation is very, very sparse, it is actually like extrapolating, right? So you want to maintain trustworthiness of the model in very sparse interpolation cases. And here, as we're looking at S22, right? So we see this very radical response by the naive scheme, whereas again, we were able to extrapolate much, much better, and we had responses that also looked much more reasonable, right? So we didn't see any erratic responses that wouldn't comply with thermodynamic consistency. So again, we could do this also in anisotropic, transversely anisotropic cases where we generated data here. And again, we had a 20% domain, and we saw that we were able to extrapolate well. And even in cases where the response was pretty complex, and we just had data from this region, we saw that we could go quite a bit further out. Of course, when your response changes quite a bit, so you see that even here we have some deviation of our model, right, from the truth, the black from the magenta. But this again is about 60% far from the training domain, strain of the training domain where we trained the model. Now, similar, so we started with this from hyperelasticity, and we thought of how to extend this in elastoplasticity as well, which is a history-dependent problem, right? So here the complexity comes from considering history, where now on top of we can have a split for our elastic and plastic strain, and then we have our free energy in an elastic and a plastic part, considering a set of internal variables, and now we have our dissipation inequality, right? Considering the rate of evolution of our internal variables and their thermodynamic conjugates. And now defining a pseudo potential also, we could get the plastic flow rule, and there are some, to maintain thermodynamic consistency, there are some restrictions to that pseudo potential, right? That it has to be convex with respect to its arguments, positive at the onset of plastic flow, and fulfills the condition that it is increasing, right? So it is going to be larger than the state that it had at the beginning. And now a common choice is to split this into a part that has to do with isotropic and kinematic hardening. And we have this F and this phi, right, where both of them are convex. And then you see they have different restrictions regarding how they are set up. So here, as we're considering this way that we are gonna have our implicit biases in our ML approach, we see that we create a modular framework for machine learning for these constitutive laws. And this, of course, is not ours, right? This has been out there for a long time, right? So, for example, one could be finding what are the hardening parameters, or finding the elastic model, or the convex model for the yield function, the plastic portion of the free energy, and the convex model for the hardening, for the kinematic hardening. And here, for example, we're going to say that, okay, there are some things that we assume that we know. We assume that we are linearly elastic. We assume that there is a von Mises criterion for the initial yield, and we have isotropic and kinematic hardenings, right? And the corresponding internal variables are this lowercase r and this alpha. So in this case, what we have to learn is we're going to learn the hardening behavior. So we're going to do some data-driven hardening. For that, we pose the pseudo potential having this yield function f, which is posed as a hypothetic transformation here. So this is in high Westergaard space for pressure independent responses, where pretty much we have to learn this function r of r. Here you can think of this homothetic transformation as a balloon expanding around an origin. And then we have also this phi, which is a function of r and x, right? So here, these are both. When we are going to do this learning, we have to understand what is the dimensionality of the data that we have, and what is the dimensionality of this target function that we're trying to learn, right? So effectively here, we made this learning a scalar valued scalar function, right? So we are just learning r of r. But here we see that we have a tensor here. So here, even if it's isotropic, you would at least have 3 invariants here. Okay, so you would at least have 4 components in here. But what we do, because we're thinking that the most typical, and this is learning in low data or limited data, the most typical data that you have for plasticity is uniaxial cyclic loading. So for uniaxial cyclic loading, we said that, let's limit this to just the squared Frobenius norm here, right? Just to learn this as a function as a scalar valued scalar function again. And so for that now, to fulfill all these requirements that we had, f has to be convex and negative, phi has to be convex equal to 0 at that point and positive. And as such, we needed to establish neural networks that satisfy the constraints both for phi, you see that this is positive, monotonically increasing and convex, with its argument, and the other one is positive monotonically decreasing with respect to its input. So for that, following Amos, who had developed the framework for input convex neural networks, we developed some networks that are positive monotonically increasing, positive input convex and monotonically increasing by controlling the architecture and the type of activation functions that are used. And also we enforce strongly the initial conditions, right? And for that, the training would be, for example, in this low data scheme, that you would have 2 cycles, the blue ones that you consider for training, and the red one that you would consider for testing, for example. And now the 2 functions that we were learning were this R of R and phi of x squared. And the green dashed line here is the extent up to which we have data, right? This corresponds to how much this has evolved during the first 2 blue cycles here. And we see that, again, what we managed to do is we managed to learn something that extrapolates proficiently. Whereas if we did not constrain thermodynamically all these functions, the learning within the convex hull of where we have training data would again be very good. So here you would have a very good fit. But the moment you would try to get out of this regime, everything would fall apart. So the moment your loading conditions are slightly different than what was occurring during the test, during the test. So we saw that if we didn't add these implicit biases and these strong constraints, you would just be able to interpolate. There would be no extrapolation capability. But actually, all the developments from the School of Rational Mechanics are done for this reason, right? So mechanics was always learning, right, with phenomenology, was always learning from low data, right? This is what mechanics was always trying to do. So, so then what we do is that we also take these constitutive laws and we can run them now in finite elements. And because these have these convexity requirements already embedded, they actually run very, very well in finite elements. I'll show you. Here we had, again, Cook's membrane, one using the phenomenological model from which we created the training data, and one the data-driven model that we learned. And we see that if we look at a Gauss point and look at convergence during the Newton-Raphson, this behaved very similarly, right, for the phenomenological model and for the proposed approach. And this was the total response for the stress norm and the strain norm during this loading for the Cook's membrane. And also, you know, another interesting thing was that if we consider that we were trying to learn that we knew the exact form of the phenomenological model, and we were trying to do parameter estimation, the interesting thing is that the new approach would learn faster from this data, and in an average sense, it would also have a lower error. Even though in the phenomenological way, you know the exact form, sometimes because you can very easily be stuck in local minima. Here, what happens with ML and this over-parameterization is that it allows you to go through that landscape and find a better solution much faster, right? So this would take us 400 iterations, and here we would learn much better, you know, about an order of magnitude better in average, and at that point about 2 orders of magnitude better prediction with our proposed approach. Now, to take this one step further, because we saw that, you know, all these convexity requirements came about a lot in plasticity, we thought of also incorporating polyconvexity in our approach for neural networks, for hyperelasticity, and this was following up to some work from Patrizio Neff as well. I mean, this polyconvexity was established by Ball, and polyconvexity guarantees the existence of a solution for hyperelasticity, and it also implies rank 1 convexity, which means that strong ellipticity holds, right? So there's not going to be any short length wavelength instabilities. And so polyconvexity means that psi now can be cast as a convex function with respect to f and its minors, the cofactor of f and the determinant of f. And also, we have the growth condition. So this is as f goes to 0 and as it expands. And this can also be cast in for anisotropic hyperelasticity. So then, using these input convex neural networks, then we also sparsify these neural networks. And by sparsifying them a lot, what we end up with is that we start with something that's very overparameterized, but then during training, it gradually sparsifies this. Okay, and we end up with expressions like what I'm showing here in the bottom. This is actually the expression from the neural network, right? So very few terms remain. And here you have pretty much embedded a library, but without choosing actually any library. The library is these hierarchical functions that show up due to the architecture of the neural network, and they have to do with the activation functions that one uses and the architecture of the network itself. So here, this is, for example, the free energy that we have for a isotropic case with respect to I1 and I2 for incompressible hyperelasticity. And we do this also for rubber data sets to extrapolate between different, here we have pure shear equibiaxial testing, uniaxial testing, and we're able to extrapolate between these. We do it for steel, we do it for these hardening laws, and you see that all these expressions that we end up with are very concise. This enables the fact that you can very easily run them also in commercial software, and also you can interpret them much easier. Now, we also do it for multi-material testing. This is some multi-material 3D printing, where we also learn from multimodal tests in tension and torsion. And then the next step is to learn from imaging data, right? So, and we're thinking to accelerate that, that we develop this transfer learning scheme where we have some simple data from which we learn an initial model, and then from that we do, with an adjoint solver, we do calibration from the DIC experiments, and then validation on some simple mechanical tests again. So here again, we start with an overparameterized neural network. We do some pre-training, get a simple expression, then go to an adjoint solver, where this one now, because it's low dimensional, can run very fast, and we fine tune this on DIC data. So the way that this is set up is it's set up as a PD constrained optimization solver for the adjoint, where we have many people call this finite element model updating, right? Where we have some discrepancy for displacement data with respect to the data from the DIC, and some discrepancy for the force data, and then this is subject to the governing equation, right? And the constitutive law in terms of the fact that it comes from a derivative of our neural network parameterization with respect to the deformation gradient. And of course, we have all these constraints and normalizations that we also add them in this problem. And for example, for some pre-training from the Ghent model, we end up with a parameterization that looks like this, right? So we started with more than 1,000 parameters and end up with 7, and then running for DIC experiments at 2% strain, 10%, 20, and 30, we see that our total loss here is reducing, but here we are also seeing how, if we match the force, and we see that we are actually starting to do pretty well, with very few iterations. That means that our joint problem just needed around 10 solves to get to something that looks converged, right? And the data that we used from DIC was like that at different levels of strain, and this was the truth for the stress data. And what we end up with for our model looks like this. And our validation now for this is that we validate with respect in another test, right? So uniaxial test, biaxial test, and simple shear. And we see that the truth is the red one, where we start from is the F-all, the blue one, and the yellow one is the one updated from the adjoint. And we see that when we are at low strains, this doesn't update very well. But as we go to higher and higher strains, 30%, that pretty much we get a really good match in unseen stress states. The interesting thing was that here we had rich information for the training, right? Because you had all this stress, strain field, and the corresponding force. So here we have all these capabilities now. But what is the next step? So all these models were local models. But now as one goes to more complex materials, like architected materials, there are length scales that now come to play in the behavior of these. So for example, here I don't have this is a new plot that I made, and it's in a new paper that is on arXiv from a few days ago. These are some plots. I'll say this from Katia Bertoldi's group, showing the elements, for example, of an architected material. So these are just some ligaments, and the force displacement response that they can exhibit depending on how they're connected within this material. This is the stress response for a polyester urethane foam from Stelios Kyriakidis' group at UT Austin. And you see that this has initially this is compression, and we see that this has some linear response. Then there's a limit load. You see that this drops a little bit, and then there's a plateau, and then there's some densification as we start really pushing. This is some work by Prashant Purohit on carbon nanotube forests, where again you see this 3-stage response as well, but also a significant hysteresis loop as you go back. This is work from Sandia National Labs on some polyurethane foam, where again you see a very similar response. In this one, you see that there's actually quite a significant difference with respect to the work from Kyriakidis. You see that there's no limit load up here. This is more like a response type behavior. This is some work by Pablo Zavatieri, where you have different type of hysteresis loops in these architected materials. So creating metastable metastable states or bistable states. And this is one more work about origami-inspired metamaterials, where you see that you have again these unstable responses. So these materials have these representative volume elements, right? For example, this is some work that we did a few years ago on collagen-based architected materials for cartilage replacement, where you see that this is a plug that is embedded in the cartilage, and then this is compressed on the top. And as it is compressed, actually, these are CT scans. You see that as this is compressed from the top, there's a densification front forming radially now. So you see a cell in the interior that remains pretty much intact, right? Whereas the cells on the exterior that are in yellow have collapsed and crumbled a lot, right? So this shows that there's almost like a phase change in this material, that there's this zone that is really densified, that is radially outwards, and in the interior of the material there is this other phase where the pores are still open. So in these architected materials, you have the size of these RVs that matter, but also these multiscale cascade of instability responses that really guide how the material is going to behave. So the way that we start modeling these, and these are things, for example, we had started working on this for local model, using local models for and machine learning to see if we can get something, and we were seeing that we were using more and more ML tools to try to capture the responses, but we're seeing that fundamentally we couldn't get what was happening in the material. So we decided to take a step back and try to rethink of this problem from the continuum mechanics perspective to see what we're missing. And what we were missing is that was this effect of the length scales, where here we consider also these non-local invariants for anisotropic hyperelasticity, where on top of I1 to IN, that were the invariants that I talked about before, now we have these locally averaged invariants. You can think of them as averaging the invariant over this non-local length scaling, right? Which in this problem you can think about as the size of the RVEs. And then starting from the principle of virtual power, we have the thermodynamic conjugates to these non-local invariants, but also to the gradients of these non-local invariants. So this is we go into gradient or non-local theories, if you want to call it that. And from these, the balance equations that we end up with is the mechanical equilibrium, which is the traditional one that you know, but also these microforce equilibrium equations for every non-local mechanism that we have, right? In which we see that what comes into play are these gradients of the non-local invariants. So now, in order to see phenomenologically how one could take the next step to model these behaviors, we see that we have some base response that is polyconvex. For example, this could be Neo-Hookean. Then we have some non-convex response. For example, this we take it from, this is a Gao-Ogden model that creates two minima. And then we have some coupling between J and its non-local counterpart. And we have some penalization of the gradients. And here, instead of the only non-local mechanism that we consider is this non-local volume ratio, J. And then we consider compression, like what we saw in the first examples. And what we see as we change the first sample is completely homogeneous. And we see that as we start compressing, this is stable. Then at some point, there's some very densified phases that form. So here you see a coexistence of the material that is 70% compressed and almost 10%. Okay, so we see Jacobian is at 0.9 and at 0.3 at the same time in different positions. Of course, here we didn't add any imperfections. And then this forms a front and completely overtakes the specimen, and then it goes into densification. So we see elastic plateau densification. And we see that, as we bias this to make it, for example, softer and softer on the top. So here we grade the material properties. We see that this can localize in one specific region. But as we'll see afterwards, what has to do with this is that the properties of these materials, because they have this architecture, they are prone to being sensitive on local properties. So what we can get with these types of models is we can get hysteresis loops. For example, here we densify, there's a front forming at the top, the front propagates, so we have this complete phase transformation. Then at 0.6, we are densified, 7, we are fully densified. Then we start unloading at 8, again homogeneous. Then at 9, we have the backwards transformation, and we create this hysteresis loop. For example, and here we don't add any perturbations, right? And if we use a different type of model for our non-convex part of the free energy, we end up with a bistable response, which means that we load, get to the plateau, densify, and then coming back, we find another minimum, right? So here, even though we remove the force, we are at this fully unloaded state. And here we saw that there's a more complex localization behavior for the formation of the initial state of the phase change. Some other things that we can capture is this global instability responses that we can control as we change the length scale to get globally coordinated instability modes, which is, for example, here you are compressing and you see the Poisson effect, but as you keep on compressing, then you see an auxetic effect where this retracts, and then once it fully densifies again, this starts. So this is only compression, right? And you see that the the Poisson effect, auxetic effect, and Poisson effect again. And for example, if we look at different levels of polydispersity in these materials, we see very different responses. So here we saw that for some limited polydispersity, we had this response that still shows a limit load, but as we increase the polydispersity and we see many more bands forming in this material, let me play it again. You see many more bands forming in this material. I'm not sure if you're seeing it very well right now.
Yeah.
Let's hope you are. Yeah.
The videos
So
actually did not play around. Can we play it once more, Nikolaos?
Yes. I'll stop it for a second just to see the bands forming here.
Yeah, it works now, I think.
I see it very granular on my iPad, right? So you see these many bands that are forming here. And when these many bands form, we see that the peak load actually is removed. So here, there's almost two levels of, and I'll stop the other one to see that here in the left, pretty much one big band formed. So here, well, as one thinks of problems like this for machine learning, one has to understand that it's not just the constitutive law that one picks, but it's also the distribution of material properties. It's the selection of the length scales that come into play. So I think that some of the problems that we have, and there's many problems that are like this, right? For example, fracture, cavitation, instabilities. These are as we try to tackle more complex problems that are multiscale, right? For example, this is a continuum model for something that has behavior that is governed in a multi-scale sense. There's more and more open questions for machine learning, right? So this is not some trivial ML extraction of just the simple closure. This has to do with identifying length scales, identifying spatial variation of material properties, identifying the underlying constitutive law. So our next tools that we're developing have to be able to tackle these problems that become more and more complex as we want to uncover more and more complex behaviors in architecture materials. So just to close this, we explored the possibilities for constitutive modeling and closures for solids with machine learning while our main goal was to maintain trustworthiness. We explored the low data regime and balance between generalization, interpretability, and expressivity. And this was all for local models where we didn't see instabilities, we didn't see localization, we didn't see complex responses. We saw some richness due to the non-linearity of the processes that we were trying to capture, though that is non-trivial. But then as we looked at more complex materials like architected metamaterials, we saw that there were effects like local densification, microscopic instabilities, hysteresis loops, multistability, polydispersity. So these types of problems now open up another set of questions that we have to see how SciML is going to answer in the next few years, and how we can develop robust and efficient approaches. For example, can we combine some elements of what we developed from model extraction from DIC, these transfer learning approaches to close the loop as one tries to understand architected materials and model them at scale? Because so far, what we have is that people, for the most part, develop discrete models for these architected materials, which end up being very limited in size with respect to what one can model. And if you do homogenization in this case, especially from a local approach, then you cannot capture localization in a phase front because your periodicity assumptions mean that there's multiple fronts actually. So there are many open problems. We have started scratching the surface with some of the SciML tools that we are developing and redesigning for computational solid mechanics, but I think there's also a lot more work to do in the future. The majority of the work that I showed today was from a former student who's now an assistant professor at UT, Jan Fook, but also from Sarvesh and Mohammed, Stephen and Kira, who are postdocs in my lab, and also Govinda, who was a former postdoc now at EPFL, and also collaborators from Sandia, Lawrence Livermore, Colorado Boulder, and Los Alamos. With that, I'd like to thank you, and if you have any questions, I'll be happy to answer.
Thank you, Nikolaos. That was amazing.
Thank you.
We will open the floor for questions. Shovik, you want to start with the question, with anything that you want to ask?
Maybe go to the audience, then I will go. I have 3-4 questions, but let's go to the audience. I mean, I can always ask Nikolaos separately. Let's see if the audience has a question. If not, I will start actually. I'll ask.
I guess you break the ice.
Okay. So hi. Yeah. So in the first part, right, where you're using the GP and GP was giving very good results, right? Were you also capturing the uncertainty and trying to propagate that, or were you only interested in the mean?
No, we were not doing that. We were not doing that at that point. So we were just we were doing it for zero noise, for example.
Okay.
Yeah.
Okay. Yeah.
More recently, to answer this question, more recently we have with Govinda, we went back about thinking about GP and thinking about Bayesian approaches to propagate uncertainty and to keep track of uncertainty in these models. The question for me there is that, and we have recently been doing some work with interval approaches actually, which take convert this problem from a probabilistic to a deterministic setting, right? For example, trying to find an upper bound and a lower bound. The problem is that, as in mechanics, for example, if you have two tests, if you have a uniaxial tension and a biaxial tension test, and you still might have the response, you still might have some noise in these tests. When you do it in a Bayesian perspective, and you think about the invariant space, and the fact that you just have two lines in your data just now lie on two lines in invariant space from these two experiments, then the uncertainty is really growing in between these experiments. Whereas sometimes what we want is we want to actually interpolate the uncertainty bounds in the from the experiments that we know. For example, you might have a lower bound in uniaxial tension and a lower bound in biaxial tension, So now the things that we're trying to do is, for example, we're trying to find the best polyconvex strain energy fit that matches the upper bound in these two, so that you can interpolate and find a lower bound for any other stress state, right? So these are the things that we're thinking about now.
Right. So the other thing is that you did that polyconvexity, and I know you did it with the neural network. But I mean, is there any way that I can impose this polyconvexity constraint in my GP? I'm assuming it should be through the covariance kernel or something like that.
Yes, but I think you would only be able to do it pointwise, only at training points, right? Whereas the nice thing for the ICNN is that it's globally polyconvex.
Because of the soft plus, I guess.
Yes, I mean, so what you have to do is that you have this architecture that's a little specialized, and then you need to pick activation functions that are monotonically increasing and convex, and that's how you maintain polyconvexity with respect to the arguments. But the architecture is also a little specialized, right? So this is a nice paper by Amos in 2017, right? So it's called Input Convex Neural Networks.
Yeah, the ICNN, right? The ICNN. Now regarding the plasticity part, right? So in plasticity, one of the problems that we are recently facing is actually when we are trying to model the softening part. At least with FE, the softening part, its convergence is a big headache.
Yes.
I mean, it's in short. So do you see some way that neural network can help in accelerating that, at least the convergence of the softening part of the elastoplastic model? Or I mean, I don't know.
No, I mean, I think that's a good point. That's a good point. So that was pretty much the whole point of this talk, to say that, okay, we've done all these things where we show, you know, I show this plasticity responses, and this is for things that are prevalent in mechanics, but also you see that the problems that we did in this first part are not the hardest parts, the harder problems, right? In what I showed for architected materials, you see the responses are way more erratic. For example, you know, you go up here, something goes down, then you have a plateau, then it goes up. Things are much more complex, right? So when you have localization, so this, for example, is something where you might have to set up with a gradient model, try to find that length scale, so that at least the behavior becomes more so once you start thinking of these non-local models, the behavior is more is regularized, okay, and you don't have mesh dependence, you don't have other issues, so it is this is one way to go about it. For example, if you just want to do some for example, in what I showed here, plasticity, we assumed that the function that we were learning for R, this R of R, was positive and monotonically decreasing with respect to the output. This was because you're thinking of this isotropic hardening as a balloon that's growing, right? So, and we only allow it to keep on growing. But for example, you could if you drop that, you also allow it to retract. But then there's other considerations in the thermodynamics as well, right? That one has to keep into account, right? So it is, for me, this is the next step, right? So going away from just fitting things that are stable and well behaved to fitting things that are unstable and, you know, actually are the critical questions in mechanics.
Yeah. And the last one is again in the origami and kirigami. In UTS it is origami, but origami and kirigami, I find both of this very interesting. I mean, the fact that you can fold or cut to change the property, right, locally or whatever. So,
to be honest, just a preface. The materials that we had in mind more were foams, right? So I'm not going to say that we had. So here, and that's why these are random foams, right? So it's not that they have a very ordered microstructure. They have cells, but they are not. They might be anisotropic because of the foaming process, but it's not that they have. Usually, they don't have also some strong anisotropy like these architected materials. For example, the model that I posed here, even though here I start with a more generic setup for these non-local mixed invariants for anisotropic hyperelasticity, the model that I ended up with had just J tilde, right? So, which meant that I didn't have any transverse anisotropy or I didn't assume any strong anisotropic character. We just had isotropy. But go ahead. Right. I just wanted to mention that.
Yeah. And you are only learning the response, right? I mean, what I was thinking that you are not worried about at this point, at least about designing. Say, how should I fold it to get a target property or something like that?
Absolutely right. But the some of the things that we're doing now is trying to learn, for example, energies that govern the instability based on microstructures. Okay. So, and then if you start understanding that, then you can go with some adjoint approach. You can also go back and do design if you have some target properties like what we showed before. So these are some problems that I find interesting these days to go forward and push. You know, I think all the tools that we have developed are really going to help us learn in a more robust way.
Right. No, this is interesting. Yeah. So that's all from my side. Like, the audience again. Sumruti, you can go ahead.
Yeah. I do want to ask a couple of questions, but I think I'll hold on because we are already past the time. Okay. If we don't have any questions, Nikolaos, I just want to quickly ask you about the transfer learning framework that you presented. Yeah. In this one, so So what I understand is like in your training of the transferred model, you are like you are retraining with a very small amount of data. But are you changing anything in the network or in anything in the loss function that you're adding
So
or
so that's
anything?
a so here I didn't talk about it just because I was brief. So here, for example, I showed this simple case where I say that in the pre-training we end up getting a very simple expression, right? So this is our network now, okay? And you see these hierarchical functions that show up due to the architecture of the network. But this is the sparsified network now. This FNN is actually the analytical expression from the sparsified network. Now, we are actually working on some schemes on how to enhance it. For example, if you see that this is not behaving well, what do? So then we, instead of going top down, which is this direction from something that's over parameterized to something that's sparsified, going the other way around. So how do I actually enhance this analytical expression? This network actually is a library of functions that are very, very similar. Okay, so and you can see you can think of something that goes directly, something that goes directly to the output, something that passes from an intermediate layer, some things that connect. So you can construct these families of functions to enhance, right? So, and we are thinking of an Occam's rule approach with one of my postdocs, Kira, who's in the lab, and we have some results where we actually enhance this. So even though we go to 7 parameters, we then add some more. We can keep on enriching this model as if the results are not satisfactory. But the interesting thing is that still you don't need to go to optimize in a 1,000-dimensional parameter space. So still you would be 7, you would go to 10, you would go to 13, 15, 20, right? And we see that there is some improvement. Usually, if we don't see an improvement up to that point, there's something fundamentally flawed with our initial assumptions. For example, maybe we're assuming viscoelasticity where there might be viscoplasticity, right? So so this is what we've been doing to enhance this model, but this is thought about more for fine tuning, right? In the sense that you had this initial response and then maybe you didn't. It gave you something only in terms of I1 maybe, but now we also want to make it in terms of I2, or we want to have some enhancement. So once you are at this analytical form that's reduced, it's very easy to actually start adding more terms to it.
I get it.
But we were happy that this was actually working so fast, because you don't want to be, the problem here is that you have to solve an FE every time, right? And this was actually a history independent problem. But as you go to history dependent problems, for example, if you try to model plasticity or viscoelasticity, you have to integrate over the history, right, to match the response. So this is why we are thinking of this transfer learning approach instead of learning from scratch.
Yeah.
But as I think Subic has some work also in this direction where they're learning directly in the full dimensional space, and as the tools are improving, maybe these become more efficient as well. I saw that Sid Kumar from Delft the other day posted a really nice paper where they are discussing a new finite element implementation where everything is vectorized, the assembly is vectorized, you don't go into loops. Yes. And I think that developments like that are super interesting on where the future of finite elements and the connection with SciML is intersecting. Yeah. So if you haven't seen Sid's paper, I recommend you check it out. It's a very
it's nice.
I think it's his latest archive.
Yeah.
Okay. Thanks again for the invitation.
Yeah, thank you so much. I think the others will probably reach out sometime to you. Thank you, Nikolaos. Thank you.
Okay, thank you. Have a nice day. Bye.
Thank you.
See you.
Nice seeing you.